text. So with that, good afternoon, everyone. It's a pleasure to welcome you all, even if virtually, to the Master Defense number 1456 of the graduate program in computer science at UFMG. So today, Guilherme Oliveira will be presenting his dissertation to a committee which is composed of Professor Xavier Rival from INRIA Paris and Professor Arthur Azevedo de Amorim from the Rochester Institute of Technology in the US. So Guilherme will have about 30 minutes to present his work. So, and after that, we'll have a public Q&A session with the committee. Once the presentation and questions are done, the committee will meet privately to deliberate on the result of the defense. So before we begin, I'd like to thank everyone for joining us here on Zoom, especially thank Professors Rival and Amorim for kindly serving on the committee. And on behalf of our graduate program, we are truly honored to have you all with us today. So with that, Guilherme, whenever you're ready, you can start your presentation.
All right. Hello, everyone. Thank you very much for being here. Let me share my presentation. Okay, so let's begin. This is my master's thesis. It's called Certified Compilation Based on Gödel Numbers. My name is Guilherme Silva. I'm from the graduate program in computer science from UFMG. First and foremost, I'd like to thank the Defense Committee, Professors Arthur Amorim and Xavier Rival, and especially Professor Fernando Pereira for advising me in this work. So for the introduction, our work is based on the challenge of building trusted software. It's a fundamental issue that code consumers always expect the software to work precisely as the developers advertise it does. But this trust is persistently challenged by the threat of hidden or malicious behavior within the software. Think of backdoors or Trojan horses. And a way to mitigate this issue would be for the users to independently audit the software if the source code is made available, but that may not always be the case. And even if that is the case, a more sophisticated adversary could target the toolchain itself instead of the source code. So a clean source code could still result in a program with malicious behavior if the toolchain has been tampered with by some adversary. And there has been multiple approaches to enhance trust in software. I'll just go real quick through some of them. Proof-carrying code is certainly one of the best known approach. That is to ship an auxiliary artifact that demonstrates specific security properties, such as the absence of out-of-bounds memory accesses in the code. It relies on an external artifact that could be automatically proven correct by some proof assistant, but it does not address the presence of malicious behavior. Just tells that such software will comply with a security policy. Similarly, translation validation also ships an external artifact that attests the correctness of individual compiler transformations. Think of constant propagation or compiler or register allocation. And it can avoid the fundamental undecidability of semantic equivalence by focusing on specific transformations. But failing to validate the translation could be a limitation of the validation technique rather than an actual error on the compiler. And we also have verified compilation that it focuses on building a formally verified compiler. CompCert is certainly the best known example of this. And it provides strong semantic correctness guarantees, but it still does not address the problem of trusting the compiler binary itself. So these approaches have limited success in countering more sophisticated attacks, thinking of attacks on the toolchain rather than the source code. So they also have the fundamental issue of undecidability. And as such, it's still plagued by the fundamental issue of who we trust. So introduce Project Charon. Charon is the ferryman of the dead in the Greek mythology. So he oversees the passage from the world of the living, the high level, to the world of the dead, the low level. And it's a technique to certify that a program was produced as the result of translating a source program. I'm thinking of low level versus high level. And it will independently compute numbers that encode the constructs that are made present in both the high and low level representations of the same program. and we use Gödel numbering to produce these encodings. The certification will only succeed if these numbers that have been independently generated are identical. So here we have this diagram that will illustrate how it works. First, we have program PK. It's the high-level program written in a C-like language. It's compiled to PL, a low-level program that is written in an intermediate representation very similar to RISC-V. And we have cert-H, is the high-level certification algorithm. It produces the number NK, that is the let's call it high-level certificate of the program. And independently, in parallel, we can also certificate the low-level representation using another algorithm, let's call it cert-L, that should also produce a number, in this case, NL. And if both numbers are identical, then the certification has succeeded. If not, that's an evidence that some behavior is present in one representation of the program that is not on the other. The background of our work is the motivation part in specific is the reflections on trust and trust. It was Ken Thompson's 1984 Turing Award lecture, where he describes a very sophisticated attack using a tempered compiler to insert backdoors into the Unix logging program. So the first step is the insertion step, where the Trojan compiler is tempered with two backdoors. One is to recognize when the Trojan compiler is building the Unix logging program to insert a backdoor into it. And the other is to recognize when the compiler itself is being built. So it will reintroduce the backdoors into the newly built compiler, the Trojan compiler has just built. So it keeps replicating itself. Then there is the bootstrapping phase. This is the most the crucial point, where as the compiler is able to replicate itself, regardless of the source code it's compiling, as long as it identifies its compiler itself, we can remove the source code that the code snippet that introduces the malicious behavior. So even if you try to compile the compiler with a clean source code, the resulting compiler will still be tampered with. Then there is the attack, because now whenever you compile the Unix program, logging program, it will have the backdoor, such as allow access with some specific credentials. And then there's the propagation, because whenever the Trojan compiler compiles a clean source code, it still produces another Trojan compiler. As such, we call this a software supply chain attack, and it's self-replicating. And as described, it cannot be detected from auditing the source code alone. We need something more powerful. Our tool, another building block of our tool, is the Gödel numbering. It's the method that Kurt Gödel introduced to prove his incompleteness theorems. And it's a method to uniquely and simultaneously identify the operation, operands, and the relative position of some expression within the context it's present. It's a four-step process. I will illustrate with an example to make it clear, because it's very abstract as it is here. So let's consider the expression a plus b. The first step would be to assign unique numbers to symbols. So in this case, we have three symbols, a, the plus sign, and b. So we could assign, for instance, 4, 3, and 7. This is an arbitrary selection. Any number would yield the same result. Then we can map each position of the elements of the original expression to a prime number. In this case, we're mapping a to 2, the plus sign to 3, and b to 5. And we compute the base number to the power of the symbol, to the power of the number associated with the symbol in that position. In this case, 2 represents the first element, and the number that encodes the first element is 4. So the first element would be 2 to the power of 4 here, and the same goes on. Then we multiply all of the contributions, and we have this huge number, 33,750,000. This number uniquely represents this expression in the context of this encoding table. So if you, from the fundamental theorem of arithmetic, there is a unique factoring of this number, and the factoring would yield this representation in the form of the multiplication, and that uniquely represents this expression as long as the encoding table is fixed. So now let's discuss the program certification that we have developed. Project Charon, as I have previously introduced, It is made to support a large subset of this language. It's actually expressive enough to compile fact. It's a work also in software security. And as such, it supports constants, variables, including arrays and user-defined data structures. And the variable supports types. So we have integers, short, and floats. Control flow, non-recursive functions, but we have deliberately chosen not to support pointers or explicit typecasts from the user. It will compile programs to a low-level IR that's heavily inspired by RISC-V. It has the access to infinite temporary registers in addition to predefined registers, such as 0, that's a register that always contains 0 or false, depending on the context. This is in the left-hand side, the EBNF representation of the high-level language, and the right-hand side, the instruction set for the low-level representation. Our numbering schema are how we have developed the encoding of constructs for our approach. There is very similar to Gödel numbering. So it's the numbers in this table are used as exponents, as in the Gödel numbering. We have this table that each construct as the language support has a unique number. And I'd like to highlight the fact that we explicitly have chosen to mark the beginning and the end of scopes, such as in control flow or functions, because it's a key design choice to enable the inversion of certificates that I will discuss in just a couple of minutes. And once again, it all seems very abstract yet, so let me use an example to illustrate the numbering schema. So here I have this high-level source program. It's the simplest program you can write in C. It's just the main function that returns 0. This is the abstract syntax tree. For the high-level certification algorithm, we will traverse the AST and produce the numbers depending on the nodes that we visit. And this is the intermediate representation that directly maps to RISC-V in this case. And for the low-level certification algorithm, we will iterate over the instruction list. And here we have the step-by-step construction of the certificate that represents this program. We have first a symbol that represents the beginning of a function, because we have just visited the funcdef node. Then we have a number that represents the constant 0, because this is what we are returning. Then we tell with the certificate that the number 0 is actually being returned. Is it being used in the return statement? Then we visit the function definition once again, in the case of the high-level certification algorithm, to tell that the function scope has ended. And similarly, we do that by traversing the low-level representation, because first we visit this the label for the function, then the instructions that represent, we identify what construct the instructors are implementing, and then we reach the halt, or we return to the probe node kind. That means the program itself has ended. So we add the symbol that represents the end of a program for our certificate. In this case, the certification has succeeded because the right-hand side program faithfully implements the left-hand side program. A very important feature of our numbering schema is the fact that variables and functions are uniquely identified by variables and function primes, because we use this certification environment. The certification environment is the first thing we do whenever we run any of these certification algorithms. So we map the nth declared variable, considering all the variable declarations, definitions in the program, to the nth prime number, and the same goes for functions. But we use the mth and prime number to map to the mth declared defined function. But we only consider variables that are alive in the program. So if a variable is declared but is never used by any expression, we do not consider it in our certification algorithm. But functions are always added to the certification environment regardless of ever being called. And then, once again, we have this example. It's another very simple function, just the main function that declares 3 variables, x, y, and z. But and this is how we produce the certification environment for this function. Main is never called directly in the code, but we still add it to the environment, because we always map function names to variables, to prime numbers. So main is mapped to 2. But here the only statement we have in this, the only expression we have in this program is to return just the x plus 1 minus z. And so the variable y is not being used in the program. So we only add x and z to the certification environment. The source code certification, the high-level certification algorithm, as I have previously introduced, it reverses the AST and emit the adequate value from the numbering schema depending on the node it visits. And it's mostly post-order traversal, but some nodes might have a different path to follow when they are being visited. This example right here that uses how we certificate a while construct. In this case, while x is less than 10, we do this expression. We will visit first the while node itself, but the rule to certificate the while construct is to first certificate the predicate. In this case, it's the last expression, so we visit the expression itself, then its operands, then we visit the right-hand side that represents the scope of the while loop. In this case, it's assigning the variable x to an expression, and in this case, it's mostly just post-order. The numbers that we are the zeros point to is the individual contribution that each node kind will have to the final certificate, and as such, this is how we produce a certificate for the entire while construct. It's okay. Now, the machine code certification, on the other hand, it's based on the iteration over the list of instructions in the low-level IR. We also use metadata that this IR carries, such as the data section or the labels of the functions to identify functions and variables. And what we do to identify constructs in the midst of many instructions is pattern matching. This is because the same instruction can be used to implement multiple constructs. The primary example of this would be the conditional jump. We call it JZ because it's used to implement all of the conditionals the language supports. And each pattern in this context consists of a set of rules for the order some instructions appearing, or the parameters that the instructions will use, and such. Once again, the while conditional consists, for instance, of a conditional jump forward that will land in an instruction that is preceded from a unconditional jump backwards. And this is we have identified this to be the only construct that implements this specific pattern from the instructions. And we also use pattern matching to infer types of variables as our language support types. It's also encoded by the certificate. So for instance, integer variables, we use the load instruction to load the contents of the memory into a register. But short variables will not only use load, but also will truncate the value. So it will use 2 instructions instead of just 1, but implement the idea of retrieving the value of a variable. This example right here should illustrate how we use pattern matching to identify the constructs. We have this high-level program that declares a variable, and there is this while loop. This is the low-level representation of it, and this is the certificate we produce following our certification algorithm. It's very large, but I just want to focus on this snippet right here, because this is the snippet of the machine code that implements the while loop. And the way we can tell that this is a while loop is due to this conditional jump. When we analyze the conditional jump, it's one of the passes our certification algorithm uses. It will check where the jump will land. In this case, it will land, it has size 14, so it will land instruction 28. It goes from 14 to 28. But we identified that it's preceded by a jump that goes backwards. And from our list of patterns, we can identify that this is implementing a while loop. And this jump backwards is actually pointing to the beginning of the predicate of the while loop. So from this instruction, number 7, to instruction 13, we can tell that this is the predicate of the loop. And what follows between the 2 conditional jumps will be the body of the loop. And as such, we can identify each part of the loop following the pattern we have identified and certificate accordingly. A very important feature of our certification algorithm is that it allows the certificates to be inverted. So if we have a number n, and this number is the certificate of some program P, then we can reconstruct another program, we call it PC, from the number alone. And PC is the canonical form of P, and it's also expressed in the high-level language. And they are semantically equivalent. In this case, I'm not talking about semantic equivalence in a more broad way. We're calling in a very specific manner, because what we call semantic equivalency here is the fact that they necessarily compile to the same machine code. And the only difference they might have is how they store or declare variables. But the essence of the program is the same. And once again, I use an example to illustrate the point. Here we have program P1. It declares a integer array with 3 positions and sets the value of the first and the last elements as 2 and 3, respectively, and return the addition of these 2 values. And we have program P2 that's very similar, and we will compile to the same low-level representation, because it uses some data structure that has 3 fields, but it only uses the first and the last field. And it also sets the values to be 2 and 3 to these positions, respectively, and return the addition of them. And as such, when we certificate programs P1 and P2, they will yield the same number n. And if we use our canonicalization algorithm over this number n, it will produce another program that has the same essence. In this case, it also defines a data structure consisting of integers and set the values to the first and last element and return the addition of them. And this is the canonical form for both programs. And all 3 programs compile to the same low-level representation. Our work is essentially theoretical. All of the properties I've just shown are demonstrated in our paper. But we have some research questions as how the certificate length will scale with program size, and how the running time of the certification algorithms will scale with program size. The benchmarks consist of 20 programs that we have written in the high-level Sharon lang, and each program should exercise a different feature of the language, such as function calls or data structures or control flow. The experimental setup was my personal use laptop. It's a M1 Apple MacBook Air, and Project Sharon was implemented in Python 3.12.4. The first research question, we are assessing how the certificate length grows versus the size of the program. In this case, the high-level representation, the high-level certification algorithm. So the program size is the number of nodes the abstract syntax tree has. And this is the result. It's fairly linear. Another important thing to mention is that the size of the certificate in this case is the length of a string that represents the certificate in the symbolic form, because representing the number itself would be huge, as we are using prime numbers with extremely high exponents. But we can assess the size of the certificate length in terms of characters the string representation of it will have. So the product form I've shown before while discussing the Gödel numbering. Anyways, the relationship between the length of the certificate and the number of AST nodes is very linear. The correlation, the Pearson correlation in this case is 0.98. And a very similar behavior can be seen when we use the number of instructions, the number of low-level instructions a program has. In this case, the Pearson correlation is slightly smaller. It's 0.97 in this case, but still very linear on the size of instructions. The second research question is the performance of the certification algorithms. Performance in this case is the running time that we have measured using Python's %% time extension. It's for high resolution time. So we could estimate the asymptotic complexity. For the high-level certification algorithm, it scales almost linearly as well, with 0.96 correlation. But for the low-level certification algorithm, we see that it's near linear, but it's not guaranteed to run in linear time, depending on the structure of the program. The last 3 dots in the graph represent programs with deeply nested control flow constructs, and as such, it displayed quadratic behavior. Now, with some related work on this issue, one of them is the diverse double compiling technique that shares the same goal with our work, but it behaves in a very different category. It's a comparative work because it tries to detect discrepancies by building the same compiler with multiple toolchains and comparing the outputs these compilers will produce. So it assumes that there is at least one trustful compiler. But this work, on the other hand, establishes a structural correspondence between the high and low-level languages And as such, our compiler, for instance, could be used as one of the compilers that someone employing DDC could use to apply the DDC technique. There are also lightweight certification approaches, such as proof and carrying code, that have previously introduced as in the background. And there's also typed assembly language, where the idea is to produce an external verifiable proof that the compiler complies to some safety policy. But our approach, on the other hand, is self-contained and does not rely on any external solvers to show the correctness of the certificate it produces, because we leverage the regularity and reversibility properties of the compilation process. And there's also symbolic certification. Professor Revolves is one of the authors of such techniques, because it verifies the correctness by constructing and comparing symbolic representations of program semantics for both high and low level to assert that they are behaviorally equivalent. And as such, it has a major advantage, that is to support optimizing compiler backends. But the weakness is that it still relies on external proofs or solvers or trusted verifiers to assess the proof it produced. So to conclude the presentation, we have introduced the structural certification technique that does not require trust in any external artifacts to present its properties. And it's achieved through the formal layout of the compiled program. We have actually written a paper on it. It's currently available on arXiv. This is the QR code pointed to the paper. If anyone is interested in reading it, there are all the proofs of the properties I have just presented are shown there. But we acknowledge it has some limitations. First and foremost, is because it assumes a non-optimizer compiler that is also syntax directed, that produces deterministic programs from the compilation process. And as such, it may not scale naturally to fully feature programming languages, such as dealing with pointers or recursive functions. That's something we have deliberately chosen not to support. Or it might not scale with highly complex instruction sets. We're using an abstraction over RISC-V. And it does not capture deeper semantic properties. As we are syntax directed, the expression A plus B would generate a different certificate from the expression B plus A, even though they are semantically equivalent in this case. So our work does not capture this property. As for future work, we believe that extending the encoding system to support compiler optimizations would be a great direction to explore, and also to enrich the certification mechanism so it can capture semantic properties and produce more robust certificates. Thank you very much for watching my presentation. This is my contact information, and these are the links for the repository with the implementation of Project Toronto. Thank you.
Thank you.